Okay, so functions of graphs. We've looked at parabolas, we've looked at straight line graphs, yes? There are other kinds of graphs that you do need to recognise. Often things that they're being asking you to identify, or things that you should look at in order to check, see what kind of graph it is the axes intersect. So in other words, where does your graph cross the x and the y axis? Gradients of them, obviously that's mainly for straight line graphs. Turning points, they're those maximum and minimum points we talked about for the parabolas, yes, the vertex. Did we talk about in these words? Have we mentioned these words? Yes? Did I mention turning points? Did I say it's the maximum point or minimum point? Yeah. Okay, good. So that's just another phrase for them. Values of x where the functions do not exist. Excuse me, we talked about that there. Remember, so when there's a fraction, remember the bottom cannot equal what? 0. Okay, so that's where the functions do not exist. If there are asymptotes, so this is a kind of a gap where the graph doesn't exist. So it's linked to the step above. So it's a gap where the graph does not exist. I will show you specific types of graphs that have asymptotes, help you identify them. It's very difficult. This is a very broad topic. The textbook doesn't cover it in a great amount of detail. So it's always a bit of a hit and miss as to the kinds of questions that they might ask you. So I'm going to go through it quite quickly. So some of the things in the packs I've given you at the moment, we're going to miss and come back to later because I want to just get through the basics of it. But we may need to go through some extra stuff. Functions we need to recognise. So linear. Okay, we obviously know they're y equals mx plus b. Quadratic, we know that they have the highest power of x squared. Cubic are where the highest power of x is 3. Quartic, actually, I don't think we do these two quartic, so let's ditch that. Reciprocal graphs. It's where you've got something over x. Exponential graphs is where they have exponents, and trig graphs. Okay? So we're going to have a flying visit through these kinds of graphs. So linear, we know these. They're in the form y equals mx plus c. M is the gradient, and c is the y-intercept. Okay, that's nothing new. Yes. What do I know about the gradient of the blue line? Positive, and the gradient of the red line? Negative. Okay, so just remember those kinds of things when it comes to straight line graphs. I'm not going to go through that because we've done plenty of work on it in the past. Quadratic. So these are the ones we've just been looking at. So that's where you've got the highest power of x is an x squared. We've got either maximum or minimum points. Remember what feature decides if it's positively happy or negatively sad? The value in front of the x squared, yeah. Okay, so if we look at the x squared, if that value of a is positive, then it's going to look like this, positively happy. And if this value of a is negative, it's going to be negatively sad. Okay? Again, I'm not going to go through that too much because we've just discussed quadratic. Cubics. Now, the tricky thing about cubics is that your basic cubic, so if you were to draw the graph of y equals x cubed, okay, it would just look like this. So it's a graph with a little kink in the middle of it. If you've got y equals negative x cubed, it just goes the other way around. Okay, so your x cubed graph on its own looks like this. However, most of them look like this. So the kink here is more pronounced. So it would either go up, or down, up, down. Okay? Similar principle to the quadratics is that if the value of a, so if the value in front of the x cubed this time, is positive, then it goes up first. So you would say up, down, up. If the value of the a is negative, you'd go down first. Down, up, down. Cubics, you may have, so this is a little summary thing here that I stole from the textbook. So we've got our general thing here where we've got ax cubed plus bx squared plus cx plus d. Okay? here is your basic one. Or no, actually, you've got the positive one or the basic one, negative one or the negative basic one. There's a lot of fancy terminology here. This translation business, we're going to go through this in a second. Or maybe this lesson, maybe next lesson. Sometimes your cubic is in a similar form to your quadratic. So if it's in brackets, then, for example, if we had something that like this, okay, there's 3 brackets multiplying together. We've done some expansion of 3 brackets last year. Do you remember that? Mm-hmm. Yes? So that ends up with a cubic graph. If we were trying to find out where that crosses the x-axis, what do you think we would do? Let me give you a clue. It's similar to what we would have done if we talked about where the parabola crosses the x-axis. We talked about that last lesson.
It equals 0?
Yes, where it equals 0. Okay, so where would this function equal 0? What values of x would make this whole thing become 0? I'll give you a clue. One of them is -2.
3 and -5.
Do we see that?
Yes.
So, -2 would make this bracket 0, therefore the whole thing would become 0. Yes? +3 would make this bracket 0, which makes the whole thing become 0. And -5 would make this bracket 0, and therefore the whole thing 0. Okay? So our values would be -2, +3, and -5. Okay?
Should we write that?
Why not? I think it might help. So I know this cubic graph here would cross at those 3 positions. It would cross the x-axis for you, to be specific. They would be the x-intercepts. Now, we would find the y-intercept in the same way as we would find the y-intercept for anything. Do you remember how to find the y? How do we find the y-intercept for the quadratic graph? So for the x-intercepts, we put the value of y as 0. What do you think we're going to do to find the y-intercept?
The x is 0.
Put the x as 0. Okay, so you would have 0 plus 2, 0 minus 3, and 0 plus 5. Okay, which gives us 2 multiplied by -3 multiplied by +5. Yes, right over that? So what's 2 multiplied by -3 multiplied by +5? -30, yeah? Now, this is a really dodgy sketch, but if you're asked to sketch something, really it's not important how you sketch it, it's important that you're showing these kinds of values. So if I knew it crossed the x-axis, sorry, the y-axis at -30, all I needed to do is do this. I can show it crosses the y-axis at -30. My scale doesn't have to be beautiful. But then we have to say, well, what do we do now? Well, we know the rough shape of it is either this or this. Yes? So it's either up, down, up, or down, up, down. We decided that that's determined by the value in front of the x squared. So if I were to expand this, without having to expand everything, the first term would be my x multiplied by x multiplied by x. Is that going to be positive or negative? Positive. Yeah, it's not a trick question. X multiplied by x multiplied by x is going to be a positive value. Therefore, this particular graph would be going up first, then down, then up. So we look at our points. We would go up, then down. It has to hit through here, and then go up again. Now, how high up you go, how far down you go, really not important for a sketch. Okay? The fact is that we've shown our x-intercepts at the correct positions, and we've shown our y-intercept where it should be. And we've shown that we know it's a positive cubic graph. Now that's a real whirlwind look at cubic graphs. Are we okay with that? Yeah? Getting a lot of
Yes.
Alright, reciprocal graphs. Okay, these are where the x is on the bottom. Okay? So these kinds of graphs always have two portions to them. They have a portion up here and then a portion down here opposite it. Okay? In some cases you will find that they do this. Okay? That's going to happen if the value up here is negative. Okay? So they're always opposite each other though. Okay, so it's either a quadrant there and there or here and here. Now, this is our basic graph with y equals something over x. So for example, y equals 4 over x. Okay? If there's ever x is on the bottom, then it's going to look like this. So if it looks in some kind of fraction, then it will have this shape. For your basic one, we have asymptotes. Now, as I said to you, an asymptote is where the graph doesn't exist. For this basic one, we have asymptotes at the line y equals 0, which, if you remember, I'm going to get the later. The line y equals 0 is this line here. So remember, the x-axis has the equation y equals 0. Did we remember that? Or it came back to us when I said it. And then the y-axis has the equation x equals 0. Okay? Those two lines are asymptotes. What that means is that my graph gets really close to those two lines, but will never actually touch them. In other words, we know that the value of x here cannot equal 0. And that's why the line x equals 0 is an asymptote. Okay? So if there's ever a time that you're saying that x cannot equal something, it means that there would be an asymptote there. So you would have an asymptote. And we generally show asymptotes with dotted lines. Okay? So dotted lines show where the asymptotes are. Now, here the fact that we've got y equals 0 as an asymptote indicates that we would never have a value or an answer of 0 here. Okay? So a number, or 4 divided by a number, will never give us an answer of 0. Okay, there's no way that you can chuck into your calculator 4 divided by something and press equals and it comes up on the screen as 0. Everyone read me? Agree with it? 4 divided by, there is no number that you can stick in there that tells us that that means it's 0, which means that y equals 0 is our other asymptote. Okay, so that's where we would have our graph. Yes?
What is A?
So A could be anything. So for example, I just chose randomly 4. Okay, it could be anything. Okay, 11, 16. If it was a negative value, that's when it would be in those other two quadrants. So if it had been negative 5, for example, it would be in these two things here. Okay. Now, I've said here, as x gets very big, so x would get very big along here. Do you all agree with that? So this is my x-axis. We know that the value of x is getting bigger and bigger and bigger here. This direction, x is getting very small, in other words, very negative. Yes? That means that the value of y is getting closer and closer to 0, because our graph, it's not drawn too brilliantly. I said here our graph gets very, very close to that line, but never touches it. So it's getting smaller and smaller and smaller and smaller. So if we had stuck a very big number into that equation, our calculator would have probably rounded it to 0, because our calculator can't work with too many decimal places. And so we would have said it was 0, but we know secretly it can never actually equal 0. So if you were to stick a very big number in, it would tell you that the answer was 0, because it gets very close to 0. Okay? If you stuck a very big negative number in, same thing, it would get very, very close to 0. Now, sometimes the graphs look a bit like this. Okay? X is still on the bottom. Okay? X is still down here. These A, H, and K, they can be any numbers. Okay? So they represent any kind of number. Our equation always will have an X and a Y. These represent other values. If we have it in this format, it means that our graph is still looking like this with our 2 quadrants. Okay, so it's still look at our 2 branches, sorry, I should maybe say. But it's shifted. Do you remember we talked about how the parabola shifts? Yes? So does any graph. Also can any graph. Okay, so this one here is shifted. I actually want to talk about that shift later when we talk about transformations of graphs. So I'm going to halt that, and I'm going to come back to it. Okay? Exponential graphs is another one we need to look at. Now, please remember that any kind of graph, if you're asked to draw any kind of graph, you can always set up a table of values like this. Okay? So if you were asked to draw something, you can set up your table. Or you have your graphical calculators, you can stick value, you can input it into there. I don't need to ask what's happened. Right, so y equals 2 to the power x is the graph we've drawn here. So we're saying that y is equal to 2 to the power of -3, which is 1/8, to the power of -2, which is 1/4, -1, 1, so on and so forth. So our graphs always have this shape, okay? There is a feature about exponential graphs in that they always go through this point here. So if they are just a straightforward y equals some value, I'm going to be consistent and use a to the power of x. So if they just look like this, they will always go through this coordinate here. Can anyone tell me why they would always go through that point there? Why would they always go through this point 0, 1? Looking at the format of the equation. So the format of the equation is y equals something to the power of x.
Because anything to the power of 0 equals 1.
Yes, anything to the power of 0 has to equal 1. So it wouldn't matter what value this was. As long as this value here is 0, it's always going to go through that point 0, 1. Yep. Okay? Now, when this value of a changes, it's just going to change how steep it goes. So it might go up a bit steeper, it might go up a bit more gently. So this is what is affected by this change, but it will always go through this point 0, 1. Now, we're going to talk about transformations of graphs as well, which tell us that it may not necessarily go through this point if it had some other number stuck on the end, or if it had some number up here. That's going to change things, but we'll talk about those when we look at transformations. Okay? Log graphs. Log graphs are connected to exponential graphs. Okay? They are reflections of them. Okay, so here is a graph that looks a bit like that one up above, yes? This dotted one here. A log graph would be the reflection of that in the line y equals x. Now, I'm pretty sure we need to know log graphs, but now I'm second guessing myself. Let me pause. Okay, so I'm just going to stick to the fact that exponential graphs and log graphs are reflections in the line y equals x. There is a connection between them. I'm not going to go any further than that because I don't want to confuse the situation. Okay. How to find x and y-intercept, so we talked about this. To find the y-intercept, you replace the value of x as 0 and solve it. To find the x-intercept, you put y as 0 and solve it. Okay, so we've talked about that for previous graphs. It works for any of them. Finding maximum and minimum points, that can be done using GDC, so we'll talk about that later. GDC, you know, in calculator. So if you're ever asked to plot them, always plot them on your calculator so you can see what they should look like, and that will catch any errors. If you're not comfortable putting stuff into your calculator, then you need to practice that, which means you probably need to make sure you're bringing it to every class and making it charged, making sure it's charged. Graphs of common functions. I thought this was a nice little summary. Okay, so if you've got y equals any number, okay, so y equals 7, 6, -2, -7.9. Okay, it would always be a horizontal line, we know that. Straight line, this is your basic y equals x. Obviously, we know most of them are y equals mx plus c. This is your basic x squared, so it goes through the point 0, 0. Your basic x cubed. Oh, didn't mean to move that. This is your basic reciprocal graph, 1 over x. Modulus graph as well. Let's kind of put a bracket around this one.
Well,
because I don't think you need to know it. This is our exponential graph we just looked at, and then this is our log one. Again, let's put brackets around this one just because I haven't seen many questions about them, but I just want to expose you to them just in case. Trig graphs we're going to talk about now. I do have a special whole pack on trig graphs, so
can you already do it?
exactly, we have that one later. Okay, so let's move on to that so we can talk about those as well.